Today I'll be showing you how to perform a motor burn simulation within Romans. So click on the Motors tab, click Motor Burn Simulator, give the simulation a name, call it Test Motor, and we'll add some grains. So click on Add, select your propellant. We'll just use standard rocket candy. It fills in all this information it got from the propellant record. Type in the grain diameter, so we'll make it 17.1. We'll leave the grain length blank at the moment and select the geometry as a cylinder, fully cored, 6.5mm core diameter, and click on the neutral button. That'll create a neutral burn grain. Calculates the length for a neutral burn grain. We'll inhibit the outside surface and we'll add 2 grains. And there they are. Next thing you want to do is select your condition. Typically you want to start off with a chamber pressure. You want to select the maximum chamber pressure that the motor is going to perform at. We'll select 2.5 megapascals. And we'll give it an initial throat diameter. It doesn't matter at this stage because it'll work out the throat diameter needed to get the maximum 2.5 megapascals. You can add in throat erosion. We'll leave that blank at the moment. Your chamber efficiency, nothing's 100% efficient. You're always going to have heat losses through the walls. Same with the nozzle. If it's not perfectly formed or smooth, you'll have a decrease in efficiency there, so 95% is about a good value. The flame propagation delay is the delay between the ignition between each of the grains. We'll just leave that blank at the moment. Chamber free volume is the excess volume apart from any free volume within the grains itself, so that typically will be the volume of the throat. So we'll just put in a small value for that. And this reduction in chamber pressure build-up rate, it reduces the rate at which the pressure builds up within the motor. We'll leave those blank and we'll show you how they affect the simulation in a minute, and just do a calculation. And you can see it generates the standard Bates grain profile, this nice flat curve up the top there and steep sides. It says it's an E50. And for a maximum pressure of 2.5 megapascals, we need a throat of around 4.5 millimeters and an exit diameter of around 10. So we'll go back up here, we'll select exit diameter, put in 4.5 as the throat and 10 as the exit, and calculate again. Now let's put some throat erosion in. Say we'll add 10% throat erosion, and we'll put a 5 millisecond propagation delay and calculate. You see that it's moved it down slowly as the throat erosion occurs, and it's moved the initial build-up pressure to the right a bit. The curve is starting to look close, but not quite the same as an actual burn of the motor. This is where this reduction chamber pressure really comes in here. Now for a Bates grain type motor, it's around 0.5. For an end burner motor, it's about 7. And you'll see what that does, and that'll reduce the initial chamber pressure build up and it'll move it across. Now we're starting to get that smooth curve that you see typically when you do a static test. Okay, so we'll save that motor. Now once you've created your motor, you can use that within the flight simulator. So say we had a rocket, we want to fly that in, 180 grams, 34 outside diameter. You can add in launch altitude and different drag coefficients and initial launch velocities. We'll just leave those. Use results, and click on calculate apogee using calculated thrust values. So for this particular rocket, it'll hit apogee at about 7.5 seconds. Okay, so what if we want to add a delay grain in now? So we go over here, click on add, and we'll use a different propellant. The great thing about this motor burn simulation is you can mix different propellants, different geometries, and it'll do the lot. I'll add a delay grain with the same length as the web width of the base grains. So we'll give it a diameter of 10 and grain length of around 5. It's an end burner, so we'll just inhibit the outside surface. And what that'll do is add a little bit of thrust to this actual motor, so we should see that change a bit. So it's just gone up slightly. Now we want to add a delay grain of say 7 seconds. We'll use Caro again, corn syrup. Now the corn syrup rocket candy burns at around about 2.7 millimeters per second at 1 ATM. We want 7, so let's make it 19, a length of 19 millimeters. It's an end burner, so we're not having any core geometry, and we'll just inhibit the outside surface and add 1 grain. Now we want to add the ejection charge. Select black powder, add some sort of length of ejection charge in there. We won't inhibit it, so the whole thing will just go at one go. We'll add. So now we'll have the 2 base grains, the end burner, the delay grain, and the black powder ejection charge. Let's see what happens. And there it has. There it's simulated. So that's pretty well spot on. About 7.5 seconds. Yeah. So that's worked well. So we can save that. And if you want to fool around with the grains, you can actually select them, delete them, do a recalculation, and if you want to set it back to its initial point after you saved it, hit the reset and it's all back to how it was initially. So let's just delete that, delete that, delete that. Let's just change one of these base grains to something else. Let's make it a partially cored grain, and we'll give it a core length of 14 millimeters. See what effect that has on the motor. So we have a full base grain and a partial cored grain. So you can see that the full core's burning and then drops almost down to nothing. Well, let's change that propellant to something that burns a little bit quicker for an end burner, say black powder, and see what happens. There's the initial burning of the Bates grain plus the black powder. Bates grain dies off and it becomes an end burner. So it's extremely powerful. You can mix and match different geometries and different propellants, and it'll work the lot out for you. So how accurate is this? Let's have a look at a actual simulation of a motor that was run under static test. So let's have a look for a static test of that particular motor, that one there. So there's the static test. Let's compare them. So there's the simulation and there's the static test. So they're looking very, very similar curves. And the values, maximum thrust for the simulation is 8.16, 8.17, average 6.6, average 6.8, E65, E65. So it simulates it very well. Okay, I think that'll do for today. Might have a look at static testing in the next video. I've just brought up the static test screen, and that's just connected to my mic, so all this stuff you're seeing is just my voice. Okay, thank you for watching.